In physics, when we deal with falling bodies, we usually simplify the problem by saying that air resistance is negligible or even equal to zero. So a body that's falling has uniform acceleration. But then we also learn about terminal velocity, and we understand there is air resistance, and that we expect the velocity of a body over time falling through a fluid, such as air, to do something like this, to some constant terminal velocity, let's call it Vt. We should be able to get an equation for this graph. Certainly in A-level physics we can do that, but we have to make some assumptions to make it more, well, manageable as a problem. So the first assumption, we're going to assume that the ball is small. We're going to assume it's small because the smaller the ball, the less we have to worry about chaotic airflow, turbulent airflow, perhaps I should say, and we can just deal with the laminar flow of air around the object. And that does make it much easier, because air resistance, well, there's different ways of modelling air resistance. One way is that the air resistance increases with the square of the speed of the object through the fluid. That's fiendishly difficult to solve. But another way, which is true for small spherical objects, uses Stoke's law. Now, Stoke's law says that the air resistance is going to be equal to 6 pi eta RV. And put the letters in a different order if you want to, but there we go. So what is eta? Well, that's the viscosity of the fluid that the object is moving through, in this case air. R is the radius of the object. The 6 pi just falls out of the geometry somehow. And V is the speed that the object moves relative to the fluid. So you can easily calculate what Vt is by equating this to this. V will equal Vt when mg equals 6 pi eta RV. So, no problem. But there are situations where you're falling at a speed less than the terminal velocity, and at those sorts of speeds, we're still accelerating. So let's write an expression for the resultant force. The resultant force acting on this object, let's say that it is mg, so we're taking down as our positive direction, minus 6 pi eta RV. Let's say that. So Stoke's law and the weight of the object. That's fine. Well, that's going to be equal to ma. Okay, the resultant force is going to be equal to the mass of the body multiplied by its acceleration. So we have this equation here. Now we know that the acceleration is the rate of change of velocity. So we can change the acceleration for dv by dt, and that's equal to mg minus 6 pi eta rv. So there's our equation there. Hopefully you can see that okay. And if we wanted to get dv by dt as the subject, well, we just divide through by m. So dv by dt is equal to g minus 6 pi eta r over m multiplied by v. You get something, it's not quite straight, but you get something like that. Now that is a linear first-order differential equation. It's a first-order differential equation because it's d by dt, not d squared by dt squared. And it's a linear one because the v term is not squared or anything, it's raised to the power of 1. So that's a linear first-order differential equation. And there are solutions to these. You can just look them up, solutions to the linear first-order differential equations. But one solution involves inventing a new function for v and then solving that. It seems like a bit of a long way around of doing it, but it does work. So let's work our way through this, solving this linear first-order differential equation. So let's invent a new function. Let's say v is equal to, now I need two letters that I'm going to multiply together, two functions I'm going to multiply together. I can't use u and v, which is what we often use in mathematics, because I'm using v for my velocity already. So that's not going to work. Can't use a and b because I'm using a for acceleration up here. So I'm going to go ahead and use alpha and beta. Greek letters, yes, but that's because I'm just running out of letters. So I don't know what alpha and beta are, it doesn't matter. The product of alpha and beta is equal to v, which means I'll be able to use the product rule. The product rule is that dv by dt is going to be alpha d beta by dt plus beta d alpha by dt. So that's the product rule in differentiation. We can use that. We could actually plug this back into this equation straight away. Let's do that then. Instead of dv by dt, we've got alpha d beta by dt plus beta d alpha by dt is equal to g minus 6 pi eta r over m times by, well, it's not v anymore, is it? It's now alpha beta, because we've decided that v is alpha beta. So there's our expression there. Now, it seems like I've gone a bit far away from trying to solve for v. That's what we're trying to do, isn't it? Get an equation that shows v as a function of t. There's no v's in this. Don't worry, trust me, we'll go with this. I'm going to keep this constant 6 pi eta r all the way through this, rather than replacing it with something else, or 6 pi eta r over m. I'm going to keep it like that rather than replacing it with one constant, because I want to show that all the time that this goes back to this idea here, that mg equals 6 pi eta r vt when v is the terminal velocity. Okay. So there's my equation, my differential equation to solve. What can we do? We can gather terms that have alpha in it all to one side. Not terms that have d alpha, just terms with alpha to one side. And all the other terms will stick on the other side. So let's stick all the terms with alpha on the left-hand side. Let's do that. So over here we've got alpha d beta by dt. That's got an alpha in it. We've also got this term here, so I add that to both sides, 6 pi eta r over m multiplied by alpha beta. That's got an alpha in it, so I'll move that to the left-hand side. It was subtracted, so I'm adding it. Oh, that's it. And that's going to equal g, that's on the right-hand side, doesn't have an alpha in it. Subtract this term here, which has a d alpha in it. We're not bringing those to the left-hand side. There we go. Hey, I can factor alpha out to get alpha all by itself. That's cool. So alpha is going to equal d beta divided by dt, plus, and this is going to be, I'll write it the way around it is, 6 pi eta r over m multiplied by beta. And that's going to equal g minus beta d alpha by dt. Okay. Well, this bit in the square brackets, this is the key to solving this differential equation. This is the weird step, because I can set that to equal 0. I can choose an alpha and a beta such that this bit in here is equal to 0. I'm choosing a beta that makes this bit equal to 0. It may seem a bit weird, but we were just picking a solution. Once we know what the beta has to be to make this term equal 0, we now know what the alpha has to be, so we now have v in terms of alpha and beta. So let's do that. Let's make a little note of what we're doing. We're going to set that to equal 0. Now, if we do that, we could say 0 equals d beta by dt plus 6 pi eta r over m beta. But then, of course, we can subtract this term from both sides. So I'm just going to write it in one step. I'm just going to write d beta by dt is equal to minus 6 pi eta r over m multiplied by beta. So we've got that term there. If that bit in the square brackets equals 0, then that is true. If that equals 0, that is true. Well, I can solve this. I know how to solve this. Let's get all the betas to the left and anything that's not beta across to the right. So if we do that, we end up with 1 over beta d beta equals minus 6 pi eta r over m dt. And that's a constant, 6 pi eta. Eta is the viscosity of air. R is the radius of the object that's falling, spherical object that's falling through the fluid. M is the mass of the spherical object. That's all a constant. So when we put our integral signs in, like this, the right-hand side, very easy to integrate indeed. That just becomes minus 6 pi eta r over m multiplied by t, because the integral of dt is just t, plus our constant of integration. So we know what the right-hand side is. I might as well just write this in. 6 pi eta r over m multiplied by t plus some constant of integration, which we'll worry about later. Okay, well, I'm going to run out of room here, so let me put this down here, like that, so you can see the bottom of it. You can see the whole page. Fine, okay, so how do I integrate the left-hand side bit here? Well, this is just a little aside. Let's not forget that if I had x equals e to the y, just like that, another way of writing that would be that the natural log of x is equal to y. That's what that means. Dx by dy, you probably remember from basic calculus that if you differentiate an exponential function, it doesn't change, just like that. And of course, ey is x, we know that. So if I rearrange this, I end up with, let's just do it on the same line, I end up with 1 over x dx, that's all the x terms on the left, is equal to dy. And if I integrate that, the integral of dy is just y, and y is the natural log of x. Natural log of x. So that's why we can say that the integral 1 over x dx is equal to the natural log of x. That's where that comes from. So we can use that on this down here, where we've got our 1 over beta d beta integrated. Well, that's just going to be natural log of beta. Right, let's do that then. So we have the natural log of beta, and all the constants of integration, I'm just going to put all together in the same c. I'm not going to bother having multiple c's for that. I'm just going to put them all together in the same constant. So natural log of beta is going to equal minus 6 pi eta r over m multiplied by t plus some constant of integration. Right, so far so good. Now what can we do? Well, we don't want natural logs. They're uncomfortable. Let's raise the whole thing as the power of e. So this to the power, e to the power of this is going to be equal to e to the power of this. Well, of course it must do, because this equals that. And e to the power of the natural log of beta is just beta. And e to the power of that noise there is going to be e to the power of that times e to the power of that. It's the laws of logs. So e to the power of c times e to the power of minus 6 pi eta r over m t. Like that. So we have our equation for beta. And remember, this is the beta function that makes what's in the square bracket equal to 0. That's what's special about this beta function. Well, what's e to the c? Well, when t equals 0, this term becomes 1. Anything raised to the power of 0 is 1. That term becomes 1. So beta just equals ec, e to the power of c, when t equals 0. So let's instead write this as beta 0, e to the minus 6 pi eta r over m multiplied by t. It's a pretty standard thing to do, is to say that the e to the power of the constant integration is just subscript 0, indicating it is what the value, in this case beta, equals when the time is 0. Okay, good. We've got a good start. We've now got an expression for beta. We now know what beta is. So let's look back over here. Over here, we're saying that this term is equal to 0. Well, if that term is equal to 0, then alpha times 0 is equal to 0. So we've now got 0 equals g minus beta, we know what beta is, multiplied by d alpha by dt. So let's write that down. 0, which is what this term is all here on the left-hand side, is equal to g minus beta, well, that's beta 0 e to the minus 6 pi eta r over m dot t, that's beta, multiplied by d alpha by dt. And of course we can add this to both sides in order to have g equals beta 0 e to the blah, 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 blah. We can do that. We could even, once we've done that, divide through by this noise here to leave d alpha by dt. So we know what d alpha by dt equals. So let's do that in two stages. G equals beta 0 e to the minus 6 pi eta r over m dot t times by d alpha by dt. You having fun yet? I hope so. Let's divide through by this noise there. So we end up with d alpha by dt is equal to g over beta 0 e to the minus 6 pi eta r over m dot t. Of course, this is raised to the power of a negative number, so we could instead just write this as g over beta 0 e to the 6 pi eta r over m dot t. We could do it like that if that's a little bit nicer. But there we've got an expression of what d alpha by dt is. So that noise there. Fine. Well, what's alpha then? Well, let's separate out the d alpha part from the dt part and then integrate. So we will have d alpha is equal to this noise here, g over beta 0 e to the 6 pi eta r over m dot t. There's my mistake. I put dt. Dot t multiplied by dt. Now we're going to integrate that. The left-hand side just becomes alpha plus the constant of integration, which we'll deal with later. Hey, we're going to get an expression for alpha. The right-hand side, g is a constant, beta 0 is a constant, so they can come outside the integral. And then we've got this part here. So if we use, I think it's called the chain rule on this integration, we're going to have to invert that when we multiply it. So we end up with mg over beta 0. And I'm going to leave it like this. I know this is going to look odd, putting a 6 in the middle of the expression, but you'll see why. Eta r. That is there, then equals multiplied by e to the power of 6 pi eta r over m t, that's not changed, plus our constant of integration, combining the two constants of integration there. So we've got that horrible expression there. But that's alpha. And that is the alpha that, when multiplied by the beta we've got, gives us v. Okay, so what did we do? We said alpha equals two functions timed together, don't know what they are, but we decided that one of them, when we write it like this, that's going to have to equal 0, just so we could get a particular beta. And now we've got the corresponding alpha that when multiplied by beta gives you v, but also has the special case where all this noise in the middle here equals 0. So that's... the fact it equals 0 is just a mid-step to calculate a compatible function beta and alpha to give you the v. We don't care about that bit anymore. That was just a stepping stone to get compatible functions of alpha and beta. And now we can use those functions of alpha and beta because we know that v is equal to alpha multiplied by beta. So let's substitute. Ooh, hold on to your hats. Here we go. mg over beta 0 6 pi eta r multiplied by e to the 6 pi eta r over m dot t plus c, that's the alpha, now the beta, multiplied by, well, the beta doesn't have any pluses in it, so that's a bit nicer, e to the minus 6 pi eta r over m dot t. What a mess, but actually not too difficult to solve. I should put an equal sign in there. So alpha is that bit there, beta is that bit there. Alpha is the first bracket, beta is the second bracket. So v equals alpha beta, which equals that. Now, a lot of stuff is going to cancel here. But before we look at anything else, let's just see what the variables are in this equation. Actually, everything is a constant except the time. So we now have v as a function of time, which is what we wanted. It's a mess, but it's there. That's v as a function of time. If we threw that at a graphing calculator, it would give us that graph. But let's tidy it up a bit. So what can we see? Well, we've got these multiplied together plus these multiplied together. It's these two multiplied together plus these two multiplied together. That's what happens when you multiply out these brackets. When I multiply that by that, we've got e to the that noise multiplied by e to the minus that noise. So they're going to cancel. They're going to give us 1. So we end up with v is equal to mg over... And actually, we've also got a beta and a 1 over beta there, so they cancel as well, which is why I wanted to keep it as 6 pi eta r, so you could follow that 6 pi eta r running all the way through this. So when I multiply out this term by that term, the beta zeros cancel and the e to the whatevers cancel, and I'm just left with that. Now we've got c multiplied by beta 0 e to the minus 6 pi eta r over m dot t. There we go. Now let's look at a few cases. Let's look at the case where t equals 0. So where t equals 0, what do we expect our results to show? Well, we're falling. That was the case we were looking at. When we fall, when t equals 0, we expect the velocity v to equal 0. That's what we expect to happen. So let's set v to equal 0 from the equation we've got down here and look at what happens when t equals 0. When t equals 0, this term here becomes 1. So we end up with 0 equals mg over 6 pi eta r, that's that bit, 0 here equals that bit, plus, well, the exponential term here is just 1 because t is 0 and anything raised to the 0 is 1, so plus c beta 0. In other words, we now have an expression for what c and beta 0 is. We can say that mg over 6 pi eta r is equal to minus c beta 0. I just slipped that minus in there. I almost forgot it. Okay. Well, now what? Well, now let's look at a second case. Let's look at the case when t approaches infinity. As t approaches infinity, what we want is the velocity to approach the terminal velocity, whatever that is. So we can solve what the terminal velocity is by going back to here and remembering that 6 pi eta r vt equals mg when we have our terminal velocity. So that's not a big deal. We can solve that later if we want to. But this should be true. Well, what happens to our expression here as t approaches infinity? Well, as t approaches infinity, this term approaches 0. So all of this approaches 0. And so vt, v becomes vt, vt just equals, hey, that works. Vt equals mg over 6 pi eta r plus 0, because that term approaches 0. Rearrange that, you just end up with mg is equal to 6 pi eta r vt. That's exactly what I just said. That's how we can find the terminal velocity. Super duper. But let's just go back to this then. mg over 6 pi eta r, that term there, we could instead write that as vt. So we can say that vt is equal to minus c beta 0 in all our equations. We see minus c beta 0, it's vt. Fine. So now let's go back to this equation down here. We've got c beta 0 there, that's plus, so it's going to be equal to minus vt right there. And of course we know this is vt, so we now have v is equal to vt minus vt multiplied by e to the minus 6 pi eta r over m multiplied by t. I mean, that's it, we're done. All we need to do is factor out the vt. V is equal to vt 1 minus e to the minus 6 pi eta r over mt. That, if you graph it, that gives you exactly the function you expect. An exponential decay would be down like this. Look at how bad that axis is drawn. I've got a ruler here, I'm not even using it. So an exponential decay would be this, but it's minus that. It's 1 minus that. So it gives you exactly what we expect up to Vt. Absolutely brilliant. Everything is as it should be. That is the equation where we have incorporated air resistance for a very small spherical object falling through the air using Stokes' law. It was a bit of a roundabout way to get it with all the alpha and betas, but it does work. And you can chuck that in your graphing calculator if you want and see what happens as m gets bigger to this curve. You might find that interesting. Now, the problem is, in most situations, we don't actually have air resistance described as being proportional, let's put FD for the drag force, being proportional to V. In most situations, it's proportional to V squared. So a challenge to you with A-level maths and A-level physics, good luck to you, a challenge to you is to try to do the same thing we've just done there, but with V squared as a term. I mean, the standard way of writing the equation for the drag force is something like, I'm trying to remember this now, some constant related to the shape, call it CS or something to do with the shape, density, cross-sectional area, V squared, something like that, but I don't remember it. So that is the usual equation for the drag force. So we'd have mg, and upwards we'd have half CS, just a constant, rho, that's the density of the air, just a constant, A, that's the cross-sectional area of this object, just a constant, V squared. Oh no, you see it's going to get trickier. Let's go back and have a look at how we approached it last time. We said that the resultant force is going to be mg minus, but now it's half CS rho A V squared. So that's ma equals mg minus half CS rho, looks like a P, rho A V squared. So that's going to be dV by dt equals G minus, let's put CS rho A V squared over 2m. Yeah, good luck with that. You've got this horrible V squared term there. So it can be solved. What I would do is reach for the big book of integrals and use a standard integral to try to solve that. But I don't remember how. So good luck. Have fun with that.